Hi, I'm Gabrielle Smith, and welcome to the twisted world of trigonometry.
As always, we're here to keep you riveted to your screen with our dreamy looks and witty repartee.
Part 1. Angles and their measurements.
Sweet shot, boy.
Thanks.
Okay, what is plane trigonometry, and why do we need to know what it is? Well, if you look at this triangle around my head, you may say, it looks like an ordinary triangle around someone's head. Ha ha. But seriously, the three sides and the three angles that form a triangle have all kinds of relationships with one another.
Plane trigonometry is the study of the relationships between the angles and sides of a triangle. It's called plane trigonometry because the triangle exists on a single plane.
We mean plane, as in a flat, two-dimensional surface.
Now, as you probably know, triangles are three-sided figures. For plane trigonometry, we'll be looking at triangles that are flat as if they were made from thin, stiff metal. Like this baking sheet with these tasty lemon muffins on it. Notice it's not bent or curved in any way.
Section A, Terms.
In this tape, the first thing we'll do is give you a bunch of terms and tools that need to be memorized and understood.
That way, when we get to right triangles and oblique triangles, you'll be able to understand all the relationships in a triangle. And that's what Trig's all about.
I'll tell you what Trig's about. A bunch of office nerds spouting off a lot of nonsense that don't have anything to do with real life.
Actually, trig was used by Greek sailors to find their way around and meet new people.
So let's get started on some of those terms and definitions. In math, we need to use specific words that mean the same thing each time we say them. That way, we can be very precise and very clear in order to understand each other.
We have to know about angles because angles make up triangles. If we don't understand angles, there ain't no way we can understand triangles. First, we'll make an angle and name the parts of it. Then we'll show you how to measure it. So listen close. Here's some of those names and definitions that you must learn by heart.
A ray is a portion of a line that begins at some specific point and then extends forever in one direction. Remember, lines are always straight.
Check out these two rays. They both start from the same point. This starting point of a ray is called the vertex. A vertex is represented by a V. These two rays form an angle. Angles can also be straight, like this one. Let's look at all the parts that come together to form an angle.
The first ray drawn to form an angle is called the initial side. That's a pretty easy term to remember. It's called the initial side because it's the initial ray drawn. The second ray drawn is called the terminal side because it's the end of the angle or where it terminates.
A good way to think about angles is to think of the hands of a clock.
Oh, what?
The other clock.
Jeez.
Okay, now, the initial side of an angle is sort of like the hour hand. And the terminal side is like the minute hand. This little pin here, around which the hands rotate, is called the vertex.
Let's start by positioning the hands at 3:15 so that the hands are over one another. If we rotate the minute hand so it points back to 12, then the clock reads 3 o'clock. The initial side of the angle is the hand that didn't move, the hand that's pointing to 3. The terminal side of the angle is the ray which is pointing to 12. That's one angle right here. Now, if we rotate the minute hand, or terminal side, around to 5, then the clock reads 3:25. That's another angle here.
All right, so now we've drawn two angles. But what do we do with these suckers? Well, we want to measure them. And to do that, you need to know what direction your angle is going in and how far it goes. All angles are identified according to these two things. So let's identify some.
So you measure an angle by looking at what direction it goes in and how far it goes. An angle is identified by showing the direction and amount of rotation from the initial side to the terminal side.
For example, positive angles have a counterclockwise rotation from their initial to terminal sides. Like when we changed the time from 3:15 to 3 o'clock. We went this way.
So what if you go the other way? Then that means you have a negative angle. Negative angles are the opposite of positive angles.
Negative angles have a clockwise rotation from their initial to terminal side. When we changed the clock from 3:15 to 3:25, we created a negative angle. So negative angles go this-a-way.
Now we'll put these angles on a graph. You'll be able to measure them easier and grasp these angles much better that way. Because as we all know, angles don't have handles.
We'll use a graph like this one. It's called a rectangular coordinate system, or an XY graph.
This graph is made up of two lines called axes. What? Oh, axes. The horizontal line is the x-axis, and the vertical line is the y-axis. The point where these two axes intersect is called the origin. Now that you know the parts of this graph, we'll show you how to measure angles on it. Earlier, we used a clock to help us talk about angles. Let's look at that clock again.
We started by positioning the hands of the clock at 3:15. So the hands were on top of each other. We're going to do the same thing, but this time we'll put the hands on our XY graph. We're going to put both of the rays, or hands, on top of the x-axis. The vertex of the rays is at the origin of the graph, where the x and y axes meet.
When an angle's vertex is at the origin of the graph, and when its initial side is on the positive x-axis, the angle's in standard position. So, for an angle to be in standard position, its initial side must be on the positive x-axis. Now, if our angle is in standard position and the terminal side is on the x-axis, or y-axis, then it's said to be quadrantal. Let's all say that word. Quadrantal.
Okay, so our angle is quadrantal if its terminal side lands on either the x or y axis. But what if our angle is in standard position, but its terminal side is not on the x or the y axis?
Don't worry. As you can see, there's lots of space between these axes. If the terminal side of a standard position angle does not fall on the x or y axis, then we know that the terminal side must have landed somewhere in these big spaces in between the axes. These big spaces have a name.
Texas?
Nope. They're called quadrants, and there are 4 of them. Let's go back to our clock.
If the terminal side of an angle in standard position falls between the 3 and 12 hands on a clock, it's in quadrant 1.
Remember, this angle is in standard position because the initial side is always on the positive x-axis. If the terminal side falls between the 12 and 9, then this guy is in quadrant 2. In quadrant 3, the terminal side lands between the 9 and 6, and for quadrant 4, the terminal side is between the 6 and 3. So the quadrant number, and consequently the size of the angle, increase as we move counterclockwise from the initial x-axis.
As you can tell from the angles that we just showed you, some angles are larger than others. The angle in quadrant 3 is larger than the angle in quadrant 2. We measure these angles by looking at the amount of rotation from the initial side to the terminal side, and whether they rotated in a clockwise and therefore negative way, or in a counterclockwise and therefore positive way. We'll figure out how to measure these angles in our next section.
Section B, degree and radian measurement.
If you're gonna measure an angle, you gotta use one of these measurements, degrees or radians. So don't even try to use bunnies to measure angles. That's sick. Jeez.
First, we'll talk about degrees.
Degrees are measured by saying that one full counterclockwise rotation of the terminal side of an angle back to its starting point measures 360 degrees.
Let's go back to our clock.
A 360-degree angle is one in which you move the minute hand in a counterclockwise way all the way around the clock back to its original position to make a circle.
So, if 360 degrees is a full circle, then 1 degree is equal to 1/360th of a full revolution, and 11 degrees is 11/360ths of a full revolution.
There are a couple of degree measurements that we'll see a lot more of in trig.
This angle here is a 90-degree angle. 90 degrees is equal to 1/4 of a revolution. A 90-degree angle is also called a right angle.
If we move the terminal side of this angle in a counterclockwise direction an additional 90 degrees, then the angle measures 180 degrees. A 180-degree angle is called a straight angle because, well, it's straight. Duh!
Remember, Straight equals 180 degrees. Besides degrees, the other unit we can use to measure angles is the radian. A radian uses the radius of a circle to figure out the measurement of an angle. We're not going to go into the definition of a radian here. It's more important that you learn how to convert it into a degree measurement and vice versa. At some point, like when you take your test, you'll be asked to convert from degrees to radians and from radians to degrees. And fortunately for us, radians and degrees have a measurement relationship that allows us to convert from radians into degrees and vice versa easily. We've already shown you that there are 360 degrees in a single counterclockwise revolution. Now we've got a new one for you.
One full revolution is also equal to 2 pi radians.
So now we know that 360 degrees is equal to 2 pi radians.
Like we said, we won't derive the degree-radian relationship here, but we do need to talk some more about how to convert degrees to radians and vice versa. But first we have to simplify this equation. Simplifying allows you to use the equation 360 degrees equals 2 pi radians to convert from radians to degrees and vice versa. So let's simplify. We'll find an expression for 1 radian and for 1 degree.
360 degrees equals 2 pi radians. If we divide each side by 2, then 180 degrees is equal to pi radians. Now, we divide by 180 to get 1 degree is equal to pi over 180 times radians. Another way to do this would be to divide by pi on each side, giving us 1 radian is equal to 180 degrees over pi. These last two results you see here allow us to convert from radians to degrees or vice versa.
So, this one is for degrees, and this one is for radians. And this one results in mighty good French toast. And like most people, I like a good example in the morning before breakfast to work up my appetite. So let's do an example where we convert from degrees to radians. We'll convert 120 degrees to radians.
As we said, when you're given a number in degrees, use this formula. 1 degree is equal to pi over 180 times radians. The next step, as you might remember from algebra, is to multiply both sides of the equation by 120. Remember, anytime you alter one side of the equation, you have to do it to the other side too. So now multiply each side of the equation by 120. You get 120 degrees is equal to 120 times pi over 180 radians. All of the numbers in this fraction are divisible by 60. So simplify and you get 120 degrees equals 2 pi over 3 radians. Sometimes the answer is simply written as 2 pi over 3, since we know we're working with radians. So that's your answer. You know that 120 degrees is the exact same thing as 2 pi over 3 radians.
Now let's convert one in the other direction.
Let's do another example. We're given 11 pi over 12 radians, and we need to convert that figure into degrees. Here's what we do.
We've been given the number of radians, so we need to use the formula 1 radian is equal to 180 degrees over pi. Again, we're doing this because our known value is in radians. Plug that number, 11 pi, over 12 radians, into the radian side of the equation. But remember from algebra, you can't do something to one side of an equation without doing the same thing on the other side. So multiply both sides of the equation by 11 pi over 12. Next, we simplify. First off, we can cancel out pi. Then, we can reduce the equation even further by dividing 180 degrees by 12, giving us 15 degrees. 15 degrees times 11 equals 165 degrees. So 11 pi over 12 radians equals 165 degrees. That's your answer.
And that's it for conversion. Now on to the special angles. Why are they special? Because they throw great parties!
These special angles we'll see over and over again in many branches of mathematics.
Here's a list of the special angles with both their radian and degree measurements. You really should memorize all the special angles in their degree and radian measurements. But if you ever forget one, you only need to know the conversion formulas we just went over. We'll use these when we solve triangles, as you'll see later.
When we get to trigonometric functions, the measurements for these special angles will come in very handy. So wait till we get there. It'll be so exciting. Next up, we're going to look at the measurements of these angles in relation to the parts of a right triangle. So hold on to your hats.